So let me actually continue where we kind of stopped yesterday night. And we were discussing the problem of so-called Fermi polarions, single impurities immersed in the gas of fermions. This might be, for instance, in vortex potassium atom in the lithium-6 Fermi gas, or if you think about the semiconductor, it might be, for instance, an exciton in the gas of electrons. Can also be, as we discussed, could be also ions in helium-3, for instance, and there are more examples of that sort. So what I want to talk about now is how could we extract, so we did a variational answers for the Fermi polarions and try to extract some of the properties, or we wrote down the variational equations. And in this lecture I want to look into the question, can we extract now the polaron energy from what we have? That's kind of an obvious thing. But can we also extract now the effective mass of the impurity which gets stressed by a cloud of fermions? And can we also extract the excitation spectrum? And actually, how do we realize this in experiments and also measure these properties? So coming back to the lecture of Immanuel, he actually might make the point that we have to somehow characterize the interaction strength in the system. So we want to compare the interaction energy versus, for instance, the kinetic energy. We want to express things in dimensionless quantities. And in this case, we can consider, for instance, the kinetic energy of a Fermi gas is basically given by the Fermi energy of the system. And we can compare here, in this case, then the Fermi momentum, which is related to Fermi energy by kf squared divided by twice the mass. But kf is also related to the interparticle distance between two fermions in the gas, the average interparticle distance. And we want to compare this interparticle distance to the scattering length between the fermions and the impurity. You will remember that the scattering wave function, which was outside of the potential, got shifted towards the potential by a amount which was the scattering length. So we want to compare how much are wave functions shifted with respect to actually how far are fermions on average from each other. And this then gives us this dimensionless interaction parameter. It's actually convenient to plot things in terms of 1 over kf times a, so it's in the denominator, so that when the dimensionless interaction parameter becomes 0, then we actually have infinite scattering length. It's just very hard to plot infinite on the plot. I will plot infinite, so it's just a 1 over infinity, which is 0. Okay, so we want to analyze this equation which we got, which was now not written, handwritten, we cannot read it, but actually an imitation version, where we had the variation energy, and we calculated by the variation principle with respect to this wave function an equation where we have to self-consistently determine the energy of the particle. The nice thing is this can be evaluated analytically. It's a rather nasty expression, but we can do it. So if you want to extract the energy of the polaron, what we have to use when we have to solve this equation, we do this at momentum equals 0, and then we ask which energy do we get out. And if we plot now here 1 over kfa of our interaction parameter, we have very weak attraction here on the left side. And what I plot here is the polaron energy in units of the Fermi energy. And one sees one has a very tiny energy getting out of the system at weak attraction, but that makes sense. The impurities in the system, it just pulls fermions toward it, but really weak. And then as we increase the interaction strength and go over here, at some point there's a bound state developing in the spectrum. This is actually spectrum equals 0. If you actually carry on to very strong attraction over here, the polaron energy keeps on increasing. Now we can ask how far we actually got with our extremely simple variational ansatz, which we can solve on basically 4 pages. One gets this energy at infinite scattering length, 0.6 times the Fermi energy. It's actually rather impressive in some sense how much energy a single impurity can pull out at this interaction strength, even in the absence of a bound state in the system out of the Fermi sea. And then we can compare this actually to different results using different methods. And for instance, here's a diagrammatic Monte Carlo result from Prokofiev and Svistinov. For their basic clues are, you can see this really, they have all these they resum the diagrammatic series, not only in the particle channel like I thought, but in all different channels which are there. Okay, they do this 2/10 loop order, but they do this and get actually this energy. And it's not so bad, we got it right by 2% in our answers. You can compare it also to multiple particle excitations, going further basically in this Chevy-Ansatz or the Suarez-Ansatz. We can compare it to actually quantum Monte Carlo or also the experiment first performed by Martin Sierlike. And that's actually pretty good. Alright, so the next quantity we want to talk about maybe is, okay, how would actually the mass change of this impurity, this was like the raindrop basically, falling from the sky because it got too heavy. So how heavy does the Fermi boson become? We then take the same equation. This time we have to evaluate the final momentum, because we're interested what is the energy of the boron as function of momentum, and then we want to get the solution and fit basically a p-squared over twice the mass dispersion relation to it, but it's not the bare mass of the impurity, but some m star effective mass. We can put this again on the computer, solve this consistently or graphically. And what I show here is now for a rather weak interaction strength, 1 over K is -5, very weak attraction. What I show here in blue below this red curve, I show what gets out from this solution. Here's momentum versus the energy. You see a nice p-squared over twice the mass dispersion relation. And we can compare this to p-squared over twice the real mass of the impurity, and these two curves actually called inside, which just shows you that the effective mass of this boron is just really not very much different, but this is very weak attraction. So the impurity pulls only a few fermions towards it actually, like 1% or so, density increase, and that doesn't change much the effective mass. Alright, then we can go to larger attraction. We see a little bit, I mean, what one definitely sees is a shift from 0 downwards, that's the boron energy shift, and we see a very slight shift of the dispersion relation, so we get a small increase in the effective mass, and we can keep on going towards, let's say, unitarity, infinite scattering length, and there we see actually difference, that it's about 20% mass increase of this impurity in Fermi gas. Alright, we mentioned 3 quantities last lecture. This was the energy, the effective mass, and the quasi-particle weight. The quasi-particle weight of the impurity tells us how similar is actually our boron to its non-interacting state. How much is actually left of its nature, this true particle nature, or this bare particle nature. And this we can extract from this variational parameter which we extracted, alpha p, and the quasi-particle weight is just given by the square of the overlap. Again, I've got here 1 over kA versus the result which we get. And one sees this time unitarities here, actually still 80% is left of the bare impurity nature inside this boron. So it's actually very well defined, composite, very well defined quasi-particle. We had a longer discussion than yesterday. What happens when the impurity in the Fermi gas would get infinite mass, and where we argued that it's really cheap to make particle-hole excitations. And this would actually bring the Z factor for all interaction strength the whole way down to 0. And this would even happen for infinitely weak attraction, which makes it really a catastrophe, because normally we think for infinitely weak attraction can do perturbation theory. But perturbation theory would mean that the prefactor is close to 1, and that fails. And that's really showing how problematic basically infinite mass impurities are. Alright, we can compare this also to more advanced approaches like the self-consistent letter resummation, which one can do, for instance, in the framework of a functional minimization group approach. And here one doesn't see that much difference actually. actually. So we get even with our ansatz against Gaussian particle wave rather well reproduced. Good. Now the question is, okay, these are the properties, okay, this is all theory. Is there actually a way also to see this in experiments? Okay, the question is, how can we measure the effective mass? Okay, if you would have a semiconductor or so, and an electron traveling in the semiconductor, the electron would travel through the semiconductors and interact with phonons. If you want to measure its effective mass, you want to maybe to put a force onto the semiconductor and move the electrons and look at the response. How do we do this normally? We have to put electric field on this semiconductor and just pull the electrons through. It's not so easy to do in cold atoms, although we can have potentials, let's say, which would have a gradient, but what is much more simple, we could have a harmonic trap in which we collect blue fermions, and then we could put our impurity atoms in, let's say, a second harmonic oscillator confinement, which is actually put to the side of this harmonic confinement here, and then remove the trap for the fermion, and let's start to oscillate. And then one could actually see, for instance, dampening, and one could also try to extract from the renormalized oscillations which a massless particle would have. This was done so far only actually in experiments with impurities in the Bose gas. There are some experiments by Christophe Salomon who did similar things for fermions, but those were not completely conclusive so far. Then we have further methods. We can use interferometry. This is a question about, can we watch actually the wave function of the many-body system in real time, how it actually puts fermions toward it and changes its wave function. So basically what we want to really study there is the time evolution of the full many-body wave function psi of t, which would be given by time evolution with the Hamiltonian, which includes now time t equals 0, and this would be initially a fermion which is at some momentum p, an impurity at momentum p, and a Fermi C just in its normal ground state. And then you do the time evolution, you ask how is psi of t developing in time, and how does it compare actually to psi at time equals 0. And you might want to ask, how is this developing over time, a very long time? This would go to something like z times the impurity momentum p plus the Fermi C, and then comes all these corrections which we discussed yesterday. So at long times we probably approach the quasi-particle wave. This you can do in cold atom experiments. It's something which is really hard to do in solid-state systems. You take an impurity which has two hyperfine states, and we put the impurity time t equals 0 just in the superposition state of one hyperfine state where it does not interact with the fermions, and in one state where it interacts with the fermions. So we kind of created this, it's not a cat state really, but it's a state where actually the system is a superposition of seeing an impurity and not seeing an impurity. And then actually by time evolving the system, when the impurity is in the down state, actually nothing happens to the Fermi C. If it's in the up state, the impurity, something happens to the Fermi C, and we can actually watch then in real time how actually this psi of t changes in time and how does it compare to the wave function at the 0. And one can then look, for instance, what happens at very long times to this velocity. All right, there are different things we can do. We can use, let's call it, watch for changes in the medium. That's something, for instance, what one could do with single-site resolved microscopes. Let's suppose we have an impurity in a lattice system, and then we could actually just watch what happens to the atoms surrounding the impurities. Are there some correlations we can see just because an impurity is there? A different way of seeing changes in the environment is, for instance, watching for transport properties in the medium. So, for instance, if we have a pure spin-up Fermi C, and then suddenly we throw in an impurity which actually allows that when spin up at the top of the impurity, they can change their spin. Then what we suddenly would see in the medium that we flip spins in the medium. And this one can actually also do chord atoms using Ramsey schemes. And finally, this is what I want to talk about now briefly, is we can also do spectroscopy. And how would this work? We take our Fermi sea and we throw an impurity into the Fermi sea. Let's say this is a lithium-6 Fermi sea, a potassium atom. Potassium atom has a lot of hyperfine states. And using phase sphere resonances, we can use two hyperfine states where one hyperfine state is not interacting with the environment, and one state is actually interacting with the environment. So if you prepare the system experimentally first in a hyperfine state, where it's not interacting with the environment, it's just described by the non-interacting Hamiltonian, and its ground state is just given by the impurity, it's a momentum P and the Fermi sea. And the impurity is in spin state 1. But now we can use a RF pulse on the system and drive actually the system, or try to drive it into the state 2. And this is then given by a time-dependent perturbation, which basically changes the hyperfine state from the impurities from state 1 to state 2. Alright, how do we calculate this? In the most simple fashion as a theorist. The transmission rate, or the transfer rate from state 1 to 2, there's a famous formula for doing these things.
Fermi-Golden rule.
Exactly, Fermi-Golden rule. So this is what we will calculate. This is valid as a linear response. And so what it basically measures is, this is the absorption at a certain frequency. And what we have to do is we prepare the system with some initial state. We apply some time-dependent perturbation. In this case, this is our perturbating operator. We have to sum over all possible final states of the Hamiltonian in the final state of the system. And then we will always make up a delta function when we hit exactly the right energy of a final state. So how would the spectrum look like? This is now tilted around. Here is the absorption versus frequency. Okay, let's scan this formula. If the frequency hits one of the final states, we will get a delta P. We calculated one specific state, and this was the Poulron state. If you hit the Poulron state, this is an approximate, if you were really good, we would have calculated the exact wave function. This would have been an Eigen state of H. We would pick up a delta function when we hit exactly this energy with the weight or height, which is given by the Z vector. But there are, of course, many more possible final states of this
Can I ask
Hamiltonian. Sure.
So how does the width of this resonance compare to the T2 dephasing rate that you get, for example, with your Ramsey method? Because in this width, you not only have the dephasing, you also have the lifetime somehow, no? Or
sure. So what I considered here, so that's kind of a tricky question. Okay. So if you're at zero temperature and you have a delta function quasi particle at zero momentum, it doesn't have a lifetime. It's infinite lifetime, and it would be a delta function. There would be no width. And that's kind of connected to that in the long time evolution, this thing here would go just to Z. And if you take the Fourier transform of a constant, that's a delta function of height Z. However, if you have final temperature, for instance, or the T2 time, basically, which you get, gives you the width of the peak, which would be 1 over T2 time is the width in the spectrum. So what Immanuel is referring to, for instance, if you have a thermal gas, or if you have some intrinsic lifetime of the particle, then what can happen is the following. That the particle or the many-body system starts to actually time evolve, and if you are at zero temperature and we would have a very fine Poulron, in the beginning, well, it's a Fermi sea not stressed with anything, impurity not stressed with anything, and of course at T equals 0, this thing is just psi of T equals 0, so we start at 1, and then this object starts to decay. And it would go to the Z factor if you have a very defined closed particle. If you are at a finite temperature, for instance, or if you have decay, if I plot this here on the log scale, then we would get an exponential decay, and this is the T2 time, which actually Immanuel is mentioning. And this T2 time would actually give a broadening of this peak here, which just scales like how fast this exponential decay is. Right. So we can calculate this absorption factor using Fermi's golden rule. And this time, I'm sorry, I do something nasty. Here's a minus sign. So before weak attraction was here, now weak attraction is over here. It's just because experimentalists will like to plot it this way. So we have weak attraction here. We already got in the ground state the delta peak when we hit the boron energy. And this is the so-called attractive boron, which becomes more and more deeply bound as we go to stronger and stronger interactions. Now, what one, however, finds as well is when we go to stronger interactions, we find in the ground state, but we also find actually an eigenstate of the Hamiltonian at finite frequencies. And this is actually given by the so-called, or this is the coherent excitation of the system, where actually the impurity likes to push away the fermions. It's an excited state of the system. It has a finite lifetime and therefore a finite broadening. It's called the repulsive boron. And if we would have done an additional calculation, we would actually find that the Hamiltonian supports also states which are the molecular state. So here, the impurity decides actually to catch one of the fermions out of the Fermi with the molecule, and then you have basically a system where a single molecule, so in this case, we would have our impurity, we would have some fermions, and so far we consider kind of the situation where the impurity is kind of free and it moves through the system and maybe hops in quotation marks from fermion to fermion. It can, however, also say, come on, attraction is so good, let's take one of the fermions, let's build a bound state and then travel as a bound state through the system. So kind of it's a molaron instead of a molaron. Maybe that would be the right word. If we would like to calculate this, well, this was not inside our wave function. So we should choose a different wave function. Let's call the wave function M. And how do molecular wave functions look like? Well, in the center of mass frame, this would be in impurity at momentum minus k, a fermion at momentum k, total momentum 0, and they would have some envelope wave function alpha of k. And this acts on the Fermi C. And then you can ask, this is a molecular state, it's the exact molecular state if there's no Fermi C, and then it's get modified to Pauli blocking. It's actually similar to an answer which you have also in DCS theory. And if you do this, you would find that there's actually transition at some point from a boron to a molecular state. However, that we didn't do in this lecture now. Good. Now, Rudi Grimm actually performed this experiment a couple of years ago. What he did is the following. So he prepared a large lithium-6 Fermi gas, and then, so he has this gigantic is maybe too much, but he has a harmonic trap in which he fills in a lot of lithium-6 fermions, and then he uses the state-selective potential-based work, a second potential to trap in the center of the trap a very small fraction of potassium atoms. So it's a density, so if you compare here the density of the potassium divided by the density of the lithium, he had around 10%. So it's a small, it's not that small, but at least it is only about every, I don't know, 5 or 6 interparticle spacings of the lithium atom the next impurity comes. It's not perfect impurity physics, but okay, it's as good as you could get. So what he does then is he starts exactly from the scheme which we want to do here. It's called injection spectrum or spectroscopy because we inject an impurity into the system basically. So we start with a potassium atom in the hyperfine state. We drive an RF into an interacting hyperfine state, and we watch how different or how does the lithium-6 Fermi C behave, and we want to see the spectroscopically. And this is what you observed, and it looks actually very similar to what we just got from our theory calculation. The same stuff was actually done then also by Michael Köhl in Cambridge, where he actually used a two-dimensional system. Basically, he had retro-reflected laser beams, make pancakes out of light, filled in fermions in there, and the same physics in 2 dimensions. And This is actually so this line here is the one which we calculated with our Chevy ansatz, and it fits actually pretty nicely on where the experiment finds the energy of the photon. Well, no wonder we just saw that we are right at 2% compared to diagonal Monte Carlo. Alright. Now I cheated you a little bit though, because I suddenly threw at you excited states of the Hamiltonian. And we did variation in principle, so we minimized energy and got just the low state of the system. So how do we find actually all these excited states of this Hamiltonian? And how do we find their eigenenergies? We did variation in principle just for the ground state. And so the question is, how could we get there when we just work with variational wave function of this type? Maybe this actually you can also apply to different types of variational wave functions, what I'm talking about now. So we definitely have the initial state of the system in the Fermi's convoluted, sorry, this should be some size 0, which is the impurity and the Fermi. In the final state, the impurity definitely changes how the final state, otherwise nothing would happen. And then we had this type of Chevy-Surles ansatz. But now we can ask, well, this can not only describe ground state properties, but also excited states. They are approximate as well, but okay, at least one could build excited states out of this. And so let's just plug in those wave functions in the Fermi's convolution and see what we get out. So we have size 0, we start with this guy. Then we have our laser operator, or the RF operator, which takes psi 1, kills it, and makes out of it a psi 2. Then we have to build the overlap with the final state. Psi 1 became psi 2. Well, this actually works with this guy over here, but it only works with this guy if it's exactly at the same momentum. So this term cannot contribute to this overlap because that's at a different momentum. So actually what we build is that this object here just becomes this alpha p squared. And again, this is just what we called before the quasi-particle weight. That's the reason why the height of the peaks in absorption is just the quasi-particle weight. Okay, I can't even tell you anything how to calculate this. And we only had so far the ground state, just one of the states out of the whole manifold of states which you can build up with such a wave function. So one thing helps actually to get a little bit insight where these states are is if you look at the minimization equations which we wrote down yesterday. So we had two equations which we then solved. One equation we got from the variation with respect to this alpha p star, so the first part of the ansatz, and then we had the second equation from the second variation. And if you look at this, this is basically a matrix structure which multiplies a vector which has inside this alpha p, sorry, this should be alpha p, and then the alpha kq, and I could build up a huge vector with this. And then I just multiply a matrix times this vector. Here's an alpha, 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 equal to e times this vector, but that's just the solution to get actually the eigenstates, or the eigenenergies of the system. So we get a linear equation. So we have an effective Hamiltonian multiplying some vector, and we could basically diagonalize this thing. All right. The thing is that we get a linear equation system is actually no surprise, because then our wave function consists of two complete basis sets. Namely, one basis set is rather simple. It's just the zero particle hole excitation basis, the Fermi and no particle hole excitation. Then we had the second term, which was the next part, a single particle hole excitation. Let's call it KQ from now on. And what we had in front of these terms were our variational parameters, but these were completely general. So what we just built, this is a basis set, and we just try to get the optimal basis vectors basically to get the ground state, but in principle we could get every excited state. Since we have a complete basis, we actually should get a linear equation system because we have linear quantum mechanics. So basically what we did perform yesterday was actually a diagonalization in a truncated Hilbert space of zero particle and one particle hole excitations. So the question is now excited states of Then it would be just to put this on the computer and just solve it like a gigantic matrix. However, these vectors, this should have actual vector errors, so it's three-dimensional and it's rather nasty. You have to do partial wave expansions and it's not so nice. But it's a way of doing it, and some people do it this way. In more complicated settings. But we had this equation here. And from this equation we expected E. But this was, in effect, this energy we got by actually solving this equation system. So what we did calculate is the eigenenergy of the system. And we only forced now to set it to 0, and this comes from the variation principle. So the thing is, does this equation, because this is the eigenenergy, does that contain actually all eigenenergies of the system? Because in the end it's also the linear equation system, so it should contain the full spectrum because it's a solution in the end. But it's not obvious how to extract all the excited states. And here actually a hint comes from a discussion which was actually raised yesterday connected to those diagrams which you drew. So when one does a QFT approach to the system, and some of you are probably familiar with actually many by the QFT approaches, at least we had some discussions yesterday after the talk, so I want you to make this connection again. One can solve this problem also in the following way. One can calculate the so-called T-matrix of the scattering of the impurity with the fermions, which is then a repeated summation of the fermions scattering with the impurities. This was just this letter which we described here yesterday. Then we insert the calculated T-matrix in the so-called self-energy of the impurity, close the loop and get the self-energy. This was when I was saying, let's not connect this line with this line over here. It's just the connection of this line with this line which gives you exactly this diagram. And the thing is, if you do this calculation, interestingly, the ones of you who do QFT calculations, this looks very much like a bare particle propagator plus its self-energy. And that's, the formula is exactly what you get out in a QFT approach. So quite obviously, from this formula, it's already obviously what you have to do. You put this in the denominator, take the imaginary part, you get the spectrum. But let's suppose we do not know, let's say, diagrammatics in QFT, so how would we get actually this same result? And for this, we have to go back to Fermi's golden rule, and we use the following. We can actually write this delta function where there are different representations. One representation is that we write it using Cauchy's theorem. We can always write 1 over x plus some I and the small imaginary part as minus I pi times delta function times the principal value of this object. This we can insert as a definition of the delta function here. So we have to take the imaginary part of this whole object. Well then, this is just a number. We can put the number inside of this expectation value here. Then we can replace the final state energy by the Hamiltonian itself, and this is called the resolvent of the theory, or of the model. And now, well, this is a complete set of states, so we can remove the final state set. And what we just showed is that the spectrum should be given by the imaginary part of the resolvent with respect, or the expectation with respect to the initial state of the system. So, the thing is, the claim which we want to prove now very briefly is that instead of calculating a resolvent, which is really complicated, you have to build up again the whole matrix, inverted, calculate this expectation value. That's a nasty numerical problem. Or let's hope that we can prove that it's just given by this very simple expression in the imaginary part of this. And what we can use there is in the proof extremely simple identity. But it's actually helpful in many cases to actually build up, if you don't want to do diagrams and such as actually such as zero series equations, you can use these identities and they are actually very helpful. So what this is the following. Sorry, I called this theta for some. No, what's this? Zeta. But anyway, this should be the energy, so the resolvent. I write the Hamiltonian in terms of its kinetic energy and the interaction energy. So this is kinetic energy, and this is the interaction. And we can write it in terms of this expression, just to give you, I mean, it is extremely simple to prove this. Actually, does somebody see already how to prove this? I mean, I would have seen it definitely for the first couple of minutes. So what we do is we multiply this equation from the left with theta minus h. Then the first term just becomes a 1. I mean, on the left-hand side. And then we have theta minus h. I should be careful, it's from the left. Because it's operated, so you have to be careful here. It's this. And then we, from the left, we cancel again the next term. And we get t times 1 over theta minus the bare energy, or the kinetic energy operated. Oh, this is probably permanent one. Right, yeah, so this will remain. I don't know why the permanent marker would be like the whiteboard, but anyway. Good. So I cannot erase this equation. Anyway, so we have here t, and then we have, oh no, we have finished. Now we come from the right side and multiply this expression with theta minus e. We cancel this term, and we get theta minus e here. So we have theta minus e here. Here we had this cancellation, so we have theta minus h, and here it's just plus t. But minus h is just minus epsilon minus t, sorry. So this t cancels with this t, theta minus e. Alright, and that's a very powerful identity because now we can actually calculate this object. Alright, so what do we do to this end? I just want to show you this briefly because it's actually really helpful in some cases to do quick calculations. We want to calculate a resolvent, and we restrict ourselves to a certain basis set. So we have to know the expectation value of this epsilon. So if we have the zero particle Hall excitation state acting on epsilon, well, this just gives me the energy of that state, which we calculated yesterday, which was the complete energy of the Fermi plus the energy of the impurity. If we calculate the energy of the particle Hall excitation, this was the energy of the fermion above the Fermi surface minus the one below the Fermi surface and the energy of the impurity. Plus the energy of the full Fermi. Then we can calculate the matrix element of this equation with respect to 0, because that's the final object which we want to calculate. We can just plug this in. Here we get the energy expectation eigenvalue. And now we see that we have to stop because now 0 hits this operator t. So if you want to take this t hitting the 0 state, well, that's the interaction operator which will kill the impurity at some momentum p and put it into a different momentum state. But when we do this, we will find that what we just generated is exactly a one-particle Hall excitation term. So this is kind of a transfer operator from one part of Hilbert space to the other part of the Hilbert space. So we can plug this into our expression and we get our result from the equation. Unfortunately, now the zero particle Hall excitation sector is coupled to the one particle Hall excitation sector. So we have to calculate this object next. And we develop a whole hierarchy in our equations. So now we calculate this object. Here we find that 0 in KQ, if we hit this equation, here then that's eigenstates, and these basis sets are orthogonal onto each other, so this doesn't contribute. But we have this guy here. And this time we have to calculate T acting on KQ. Now this will generate two particle excitations, or it actually will kill again the particle excitation, so we can get back to the zero particle excitation sector. So we always develop the latter, we go one particle excitation up, and then we go to one less and one more, one more and one less. But we want to stop here, because we say no. We only go to one particle excitation level and stop this hierarchy of equations. And so we can calculate what T does when we act on KQ. The particle excitation sector gets zero particle excitation sectors and all kinds of different terms where we change the momentum of the particle Hall excitation. We can actually plug this into our equation, Let me actually not show these steps in the detail now. They will be in the lecture notes. But basically, we get actually we can calculate this. We will plug this into our equation for this matrix element. And what we find now is, if we write down here some collective expectation values of alpha kq, we can write this equation which we just got in a very neat form. And the equation which we got for the 0, 0 element is also in a very neat form. Here you recognize actually exactly the same equation we had yesterday in the Shelly ansatz. There we call these things the parameters alpha k prime and q. This time it's just some collective parameters. Using exactly the same methods as yesterday, we can solve this equation system. We get an equation for this half, A0. We can invert it, and we get that the resultant expectation value is this object. Well, but this object is exactly the equation we got yesterday from variation in principle. And this is exactly showing that, in fact, indeed, if you take the imaginary part of these things, you will get the full spectrum of the theory. All right. Thanks again for those who recognize this is the set energy of impurity. So again, we can do, from this very simple basis expansion, we can get the full spectrum. Although we would have thought it's just variation in principle. As long as you recognize that your variation wave function expands the whole Hilbert space, you can always do this. I think at least you should be able to always do this because it's a limitations is given there. And this is then what one did to plot this whole spectrum. We chose a certain interaction strength, let's say 2. We then plot the absorption spectrum by the imaginary part of this object. We get a peak somewhere in the spectrum. If we plot here a line, we then see a big peak and then something here. If we go to stronger interactions, we would see a peak. Then we would see a little dimple stuff here. I don't know if you like some incoherent background, which is this thing here, and then a new peak here, which is the repulsive boron, which is the good excited state. All right. And so the take-home messages with rather simple methods, one can actually, even in a strong coupling regime, describe rather well experimental results.
So, how do you understand the reforms, the equivalent background inside the previous plot? Like this continuum?
Yeah, so you know what the impurity in the end is doing as it moves through the system. We have here our fermions, and what the impurity can virtually do is it can virtually jump actually into the bound state of the problem and jump back again. And these are possible processes. Out of those you can build eigenstates of the system, but it's a whole. I mean, they can have different momenta because it's actually many particles. I mean, it's at least 3 particles in our wave function involved, and these are basically virtual excitations of actually molecular bound states which have a finite momentum and so for that reason it's often called the molecular whole continuum, this whole broad band.
In fact, just so also in the region which you have shown, there was this 3 in the molecule.
Yes.
So what does the molecule look like in the spectral equation?
You cannot observe the molecule in the spectrum if you have contact interactions. The reason is the following. The molecule is a little bit problematic to excite in some sense. So in the molecule, you would have the state where the impurity should be tightly bound to this object. But if it's tightly bound, what you would find is that this corresponds to a wave function which is exponentially localized on the scale 1 over r divided by the scattering length. So it's just the Van Kondo overlap is tiny to get into that state. And so it's a solution of the problem, but you cannot address it with eyes. So you have to do, let's say, adiabatic preparation of that state. Good. And with this, let me actually come in the last, should have something like 15 minutes or so. Let me come actually to the question. That's a nice example where we can use cold atoms to actually study in the laboratory a phenomena. Let's say, basically what we do here is we throw an impurity in the Fermi gas, and we change the spectroscopic properties or the optical properties of the system. The impurity changes optical properties, it absorbs now light at a different light frequency. It's RF, should not call it light, but electromagnetic waves. So the question is, can you actually transfer this knowledge to semiconductor devices? So the idea is, of course, or it's often mentioned in core atoms that you want to do something like quantum simulation with core atoms, design a Hamiltonian, and then realize this also in nature in a different system. And the question is actually, can we, instead of having a complicated setup in core atoms, let's actually find materials where we can get the same effect and maybe detect them. So here is actually the actual experiment is set up, okay, modulo the flow price pattern, which all this comes later. But basically here we will see, this is a system where we have a heterostructure of graphene and a semiconductor inside, which will actually show Fermi bourons. And instead of an RF, here one uses just a LED to actually see at which frequencies the system absorbs a light, which is just glued on top of this thing and then switched on. Good, so we want to study impurity uniformity with this Hamiltonian, and this should generate Fermi bourons. But what are actually the minimal ingredients to see Fermi boron physics? There are two things actually. So we want to have this Hamiltonian, of course. But to have this Hamiltonian, we need number one a Fermi C. And okay, if it's super hot, then probably it wouldn't work nicely. So let's say it should be cold, the Fermi gas. But more importantly, we need a well-defined impurity particle. And well-defined means we are not allowed to resolve its internal structure. So it should be a nice particle. And one way to resolve an internal structure of a particle is by actually just pushing on it with different particles and looking inside. Which means that if the interparticle distance in the system is actually smaller than the impurity size, then we just look inside the impurity, and then we definitely don't have a well-defined particle. So the impurity size must be much smaller than interparticle distance in the path. In cold atoms, as was discussed yesterday by Emmanuel, this is also the reason why the time scales are so slow. It's really dilute gases. Particles are super far from each other, thousands of nanometers. And the atoms, how big are they? Probably half a nanometer. Less. Like 9 to 10 to the minus 10. So in cold atoms, this is very satisfied. The question is, can you also do this in semiconductors? And in cold atoms, I will talk actually about two-dimensional semiconductors. So before we talk about if you can do something with do some quantum simulation, you should be able to do stuff also in 2D in cold atoms. That's one strength what one can do with cold atoms. I will discuss, so I discussed the system in 3 dimensions, and there we used the scattering length to parameterize interactions. We wrote down the Hamiltonian with some u, which was negative, and if u is not too large negative, we have a negative scattering length. If it becomes beyond the critical value, we get a bound state in the problem. This happens exactly when scattering length diverges. In 2D, the situation is a bit different. There every potential, attractive potential, short-range potential leads to a bound state. So for infinitely weak u, we already get a bound state with some binding energy, epsilon t. So here we can use actually just right away this binding energy to parameterize our interactions. And then one can do again this boron physics and calculate the spectrum. Here interaction strength is now measured not in units of KFA, but by comparing the Fermi energy to the binding energy. But that's just how dimensionless interaction parameter. And then one can perform, as I mentioned, the experiment also in 2 dimensions, and this was Michael Krill who did this experiment a while back. So actually here's the comparison again of the wave function which we used in this lecture. The energy of it is shown as black line versus the experimental result. Alright, so can we see this in solid state physics? And here it's really good that Emmanuel introduced the band structures. And what I show here is a part of the band structure of gallium arsenide. That's a bulk semiconductor, actually here at the gamma point. And the semiconductor is a semiconductor because we fill the valence band up to the limits of the Fermi energy somewhere in the gap. But one can actually have thermally excited electrons in the system, which makes it a semiconductor, or you can dope it. But that's basically the situation. We have a conduction band and valence band. Now if we have a laser, we can excite electrons from the valence band to the conduction band, and what they effectively have then is a hole in the Fermi here, and an electron over there. This has a positive charge effectively, and this is of course a negative charge particle. So our laser operator this time takes out of the bulk semiconductor, which has no hole initially and no electron, and makes a hole and an electron. The electron in the conduction band, the hole in the valence band. Alright, Fermi's golden rule. Basically, we have to ask what are the final states of the system. Well, one final state is exactly what we discussed kind of before. It's this type of wave function. It's a molecular state. However, we call it an exciton in semiconductors. A bound state between hole and an electron with some envelope wave function like here. Now I call it part of K. But what type of problem is this? Well, this is a negative charge and positive charge. That's a hydrogen problem, only that the proton is actually the same mass almost than the electron. So to calculate the binding energy, we have to solve the hydrogen problem. And unfortunately, when typically sets, when calculates this in vacuum, it sets important quantities than to 1. If you calculate the spectrum of the hydrogen problem, what one would find is that there's the reduced mass of the problem divided. Normally we have dielectric constant in vacuum squared, but if it's gallium arsenide, we have actually real dielectric constant squared, and then there's the principal number squared. Thing is, hydrogen of course would have a binding energy of 13 eV, but now it turns out that in a bulk semiconductor the dielectric constant is around 12 to 13, which suppresses this energy by a factor about whatever 12 squared is, and we have additionally a different reduced mass than in the hydrogen problem. And this actually leads then to a binding energy of excitons, which is just 20 millielectron volts. To give you some numbers, typical Fermi energies you can put into gallium arsenide is up to 50 MeV or even more. So this energy of the exciton is not that large. If you put too many electrons inside, let's say 50 MeV Fermi energy of electrons inside, the fermions would be closer than the size of the exciton itself. And then exciton gets destroyed. So unfortunately, you cannot use excitons in the bulk semiconductor, but typically to make large doping, basically boson fermion mixture. So the exciton is a boson, of course, consisting of two whole fermions. And now, in the last 5 minutes, I want to talk about van der Waals materials. And these are new materials studied for the last, by now 15 years. Very famously, the most famous example is actually graphene. It's atomically thin materials which you get by taking your bike, let's say, by graphite, and you with a sticky tape tear away sheets of this material, and then it's called graphene. There are, however, also a class of semiconductors out of this class of so-called van der Waals materials. So van der Waals materials because van der Waals forces hold different layers of the materials together. And that's the reason why sticky tape is enough to actually pull them apart. And examples, for instance, tungsten diselenide, and this breaks inversion symmetry, and this opens up a band gap in the graphene band structure. Now, in these semiconductors, we can then ask again, what is about going on with the excitons? And now one thing is important. In gallium arsenide, the electric field lines, they of course go in all 3D. And they always have to go through gallium arsenide. And they always suffer the epsilon of 12. But if you have a 2D material, we actually just take away most of the material. And most of the electric field lines are now outside of the material in just vacuum. So we are almost back to the hydrogen problem where we have epsilon 0. So we actually gain a lot of binding energy by this effect. And it turns out that therefore excitons actually bound at 500 MeV in these systems, so really deeply bound. Which actually makes a problem if you want to make them strongly interacting, because if they're tiny objects, it's harder to make them interacting. So we are back to that in cold atmosphere better. So these are bosons. If you want to make a large, strongly interacting boson gas out of this is more tricky. But anyway, that's not what I want to talk about now. But the take-home message is, this is 500 MeV. If you then dope the system with electrons which have a Fermi energy of 50 MeV, this thing is still well protected by getting destroyed just by density in the system. And then we can talk about, well, now we really have nice fundamental point-type boson particles inside of the Fermi sea, so we can do the same games as we play in cold atoms with boson Fermi mixtures and actually study the physics in these systems and see what we can do with this. And there's a funny, not funny, but in nice thing as well in these materials, these excitons, they can come together with an electron and actually build a bound state. That's kind of equivalent what we also have in terms of hash bar molecules in cold atoms. So they also support a weakly bound state. So that's one more ingredient which makes them interesting in comparison to cold atoms. And now, of course, we can also have just a single exciton, and then we have an impurity inside of a two-dimensional semiconductor. So instead of doing the experiment now in a cold atoms lab, we can ask, can we do this in this type of a setup where we do the following. So this was done by the group of Atachi Maboklo at ETH Zurich first, executing them actually help them a lot to actually implement the system correctly, or actually to see that there are actually Fermi polons in the systems. So what is done here? So we have a piece of glass. Actually, this is a cavity setup which is not really needed for the physics to be seen. But then what it does is the following. It has a two-dimensional semiconductor. One encapsulates it in an insulator which is called hexagon or nitrile just to secure it. Then one has to put some electrons inside, so we have to gate it. And this we can do with a layer of graphene, which you can actually charge with electrons via a gold contact over here. And this, the nice thing about graphene is, although it's a metal, we can still put light through the graphene. So we can still shoot the laser through graphene and we still hit the semiconductor. And then we can actually have the electrons in this semiconductor and try to see the physics which comes out in cold atoms. And here we tune the Fermi energy now versus the photon energy, and one finds here absorption in the system. Now here's one thing that's important to remember, and it's again about what Emmanuel pointed out yesterday. It's all about dimensionless interaction strength. In our case, this was basically Kf times A. In cold atoms, we tune the scattering length. And it's not so easy to tune actually the density of fermions. In semiconductors, we cannot tune the scattering length, but we can very easily tune Kf. And thereby we can make the same plot as we did in cold atoms, this time by tuning Kf. And this is actually what was done in the experiment. You introduce more and more fermions in the system, and then one can actually observe, actually compare to exactly the spectral calculation which we just did in this lecture, and one gets extreme good agreement also with the two-dimensional semiconductor optical response. It's kind of an example, remembering these rockets which Putin shot into the sky to get actually random polar information and get controlled by impurities of a man-in-body environment. Here one could say one used actually excitons to tune then the optical response of this semiconductor environment. All right, and this has been observed now in actually various materials, molybdenum diselenide, in molybdenum disulfide, and recently also in tungsten diselenide. And this is actually a nice starting point, so it was observed in different dielectric environments, different materials, and it's a good starting point of a boson to studying now boson Fermi mixtures. That's the most simple boson Fermi mixtures you can build, just a single boson and a Fermi gas, but now one can actually go on to more complicated settings. And the one thing with which I want to stop is maybe to have a little bit ideas of the scales in the problem. So in cold atoms we are here at low temperatures, in semiconductors, where room temperature would be somewhere here, but we are at actually rather high temperatures. And we can ask now what actually the ingredients of those boson Fermi mixtures which we want to compare between transition metal dichlorogenides, the semiconductors and cold atoms, where the fermions are atoms. In our case, in cold atoms, it's electrons in the semiconductor. The bosons, again, are atoms. In cold atoms of the size of about an angstrom, finding energies in eV. In the TeV, it's actually similar energy scales on which the excitons are bound. As we have seen, it's in eV approximately. dimensions, unfortunately, you cannot tune them in 2D materials, it's 2D. You can, however, have heterostructures. In quadratics, you can do basically whatever you want. To get tunable interactions, we use the exchange of a molecular state to get strong interactions. And the interaction energy scale is about kilohertz, typically. I mean, that's kind of the maximum which you can get. In semiconductors, it's not exactly exchange of dry, but the dry energy sets about the energy scale of the interaction strength. And it's about 30 MeV. We cannot do anything about this. Here we can do a lot about the interaction energy for that using phase resonances. What I mean by this is the ionization energy, basically, of an atom. Let's take hydrogen atom, then will be 13.6. And of course, there are different internal transitions. I mean, yeah, that's kind of, you know, just to get this. Yeah. So it's translating basically size into eV. The Fermi energy in cold atoms, they are probably up to 50 kilohertz. In TMDs, we have 50 millielectron volt, which is about terahertz scales, but that's comparable also again to the interaction strength, and here we have the same, it's comparable. And that's the only thing which matters, to make these scales comparable. And as I said, interaction parameter, in cold atoms we tune the binding energy basic, or A, in TMDs we tune KF. And this is kind of the translation table to go between Bose-Fermi mixtures in cold atoms to Bose-Fermi mixtures in semiconductors. And just this is my last slide, we can play now little games in these two-dimensional materials like we do it also in cold atoms. Then we have a whole toolbox where we can peel off different layers from different materials. Let's say, take a layer of graphene, take a layer of a semiconductor, then we take a layer, let's say, of a ferromagnet, for instance, like palladium diselenide, put them all together in the stacking which we like for the problem we want to study, for instance, electrons in one layer, in a superconducting layer, interact with excitons in a different layer. Maybe these then again interact with graphene, which has a different band structure in a different layer. It's kind of like what we do in cold atoms with different optical potentials. We can just put them together, and this gives us then capabilities to study, for instance, also tunneling between different layers. We can have twist angles between these different systems, which give superlattices, which are also studied in cold atoms. We can actually use magnetic fields to study that. We have artificial magnetic fields in cold atoms. We can study non-equilibrium, competing more with topological effects in these TMD materials. And these are all names which you also study, of course, in cold atoms, where we actually have the possibility to do a band structure engineering, which was shown, for instance, also by the Zengstock group, where we go from a graphene band structure, we open up a bandgap and get exactly this TMD band structure, and we can study the system. And we can have what Thierry wanted so much yesterday is, for instance, box potentials. And this we also have now. Actually, in these TMDs, one can also have small one-dimensional structure which one traps excitons to then one-dimensional physics. In TMDs, box potentials are a little bit more difficult, probably at the moment still, but okay. But anyway, so we have a similar set of tools in both systems. And this I actually want to stop. And this is just as an outlook of things one can do probably in the future, bringing these things together. And yeah, so it's a good platform basically both to study universal physics in the sense of my first slide yesterday. And I just want to say you can always write to me because I will only be here today. You can just come to me if you have any questions, but I'm always happy to answer also questions by email. Actually, Marcel and Jonas are also here. And you know, right, thanks a lot.
So, what's the final state of polaron versus molecules in 2D?
In 2D, the final state.
Well, because there was confusion.
No, I mean what you mean final state, not the final state of spectroscopy, but what's the debate?
Yes.
Story of the debate. Okay, I would say it's not resolved. The most state-of-the-art calculations are the chromatic Monte Carlo. This is by Louis Brulé. So, let me just say what the reason is for the question. In 3D, we wrote on the second variation equation, and what we found by this without doing it, so you have to take my word for it, is that we calculated 1 over KFA spectrum, we got the boron, and just from this very simple equation here, we got a molecule and we had a transition. In 3D, you see a transition. In 2D, with the same variation of wave functions, the molecule would actually never make a transition. So this led them first to think, ultimately there's no transition. Then there were variational wave function approaches where you take more of these terms into account, and then you get a transition which is ridiculously far out. It's at a KFA which would correspond to about 15, and this feels really unnatural. Where should 15 come from? It should be around 1. Then there were more complicated arithmetic Monte Carlo calculations, now it's around 5. So, but I'm not sure if we should trust those as well. So, what we did now is actually to do something really simple. One can also calculate this whole thing in a finite system where we can do exact diagonalization. We can put a single impurity in the system and just let it interact with 2 particles. And then the Fermi energy of the system, it's really a simple toy model. The Fermi energy of the system is given by 2 particles in a box of the size, which gives us the density. So we can increase the size and thereby reduce density. But at least we can solve the problem exactly. And there, in this case, we would get a transition at KFA around 4.5. So there is a transition in this simple.
In this case, how do you distinguish polaron from molecules?
Very good. So for this, you have to look really at the 3-body wave function structure. And you see that the polaron always consists of an impurity impurity and then 2 particles which are completely delocalized in the system, but globally only attracted by phase shift towards the impurity. But then there is the second wave function in the spectrum. So for the boron, you get such a structure. If you look at this wave function here, what we find in our exact diagonalization, that the wave function looks really like one particle is close by and the second one is far away. So you can qualitatively see the difference in the wave function. And then if you calculate the quasi-particle weight, which is the overlap of this wave function with the non-interacting wave function, you see that for this case it's really 0. And it scales to 0 as you take system size to infinity really. So it's a nice way of really seeing also what I was saying before. A polaron is an impurity which travels basically from side to side without never being really bound, while a monoron is a 2-body bound state which travels through the system, like in this case, traveling as a whole from as a whole structure from the particle to particle. Yeah, but it's still we should do more calculations. So it's so I would say the Lode-Coulomb calculation is the best so far, which is on the market.
But these 2 are at the same energies?
There are actually only 1 point at the same energy, and that's where the transition is. And otherwise there are different energies.
Other questions?
One thing. This is without Coulomb interaction. Of course, otherwise there is no molecular state.
Very cool. So I have a general question. What would one do with these polarities in terms of applications?
So, I mean, one of the applications you have seen here is you can tune, for instance, at which frequencies light is absorbed. But what you want to do is maybe in the end to think about the following. What we actually did in a recent work, we looked at the question, let's suppose you have a semiconductor, you have an exciton, and you collect all these fermions around it. Now, an exciton is a neutral particle that wouldn't see an electric field. So there's no way to move the electron via an electric field. But if the exciton gets stressed by fermions, which are electrons, we see the electric field, and the question is, do they track along the excitons? So polar information allows you actually to make them move, make excitons move via electric fields. And this applies then also to cyclotron motion. So you can actually do this. So to artificially generate electromagnetic fields, you can use boron information. Let me give one second example. What we can also study is, and that's, and I'm going to stop here. I see my mouse. Oh, here it comes. So one more thing one can also study is the following. So one can also study the following problem. What one maybe wants to do is one, okay, excitons will decay at some point and emit light. If you have a lot of excitons and they collectively decay, you would actually get collective exciton emission of light, and you want to build a laser out of this. This was done so far in two-dimensional systems, or quasi-two-dimensional systems, actually with gallium arsenide structures without electrons around, and to build exciton polarity lasers. So what one does is, one has a two-dimensional, or no, one has a semiconductor, one shines light into a cavity, couples these excitons to light, and creates exciton polaritons. Then the goal is we have an upper polariton and a lower polariton to actually send up a pump pulse, create a lot of upper polaritons. They decay to the lower polariton branch, and to get lasing, they all must go to a condensate state of Q with 0. Now, this cooling is done typically by, for instance, exciton-exciton interactions or interactions with phonons. The problem with 2D materials to get actually to get a polariton laser is you have to cool those excitons. And the excitons are so tightly bound, so they don't interact much with each other. So there's not much self-cooling of the system. So what we can do is actually to use something like sympathetic cooling, use the protons into the equivalent in TNT structures, where now we use a Fermi gas of electrons to cool down the bosons in the system, which are the excitons. And actually by this try to cool the system down. But that's then again excitons in the Fermi gas, so they actually build polons, and these polons at final momentum can decay into lower momentum states. And so you can use boron physics actually to cool excitons and hope to get actual laser gain at some point out of these materials. So actually Atachima more precise already. Without electrons, he sees a gain in the systems of about a factor 1.4. When he puts electrons inside it, he gets up to the factor of 8. Yeah, two possible applications.
Maybe just to follow up on what Richard, but much more speculative way, so it's kind of an interesting subject, why do we need tolerance? So I think one application is flexible displays. We've all read about the Samsung, bendable phones. You cannot make semiconductors advanced like traditional, so like silicon and gallium arsenide. So you have to use organic materials. And they're flexible, and they can be bent because they consist of these floppy molecules. But the same reason why they can be bent is why they have a strong electron-phonon coupling. So if you want to understand transport in organic materials, you have to study polymers. So they're known to have like very unusual chemistry dependencies. And then in connection to this specific part, I think it's, I don't know if maybe Richard already pointed this, that one of the major goals of quantum optics is to have a very strong interaction between photons, right? And that's very hard. And the whole idea is that this is a way of making excitons very strongly interacting. But excitons can hybridize with light to make a polariton, and therefore it sort of brings us closer to the goal of having very strong and nonlinear optics. It's one of the rules.
Yeah, so this case here where you have excitons, they are attracted with photons, and you can ask about can you do three-body bound states of photons basically then in these devices and do really strongly coupled actually photonic systems. The kind of stuff which we know from Rydberg gases or one would actually say. Yeah, actually there was a discussion also in the terms of this quantum biology, which now kind of broke down in the last, I think, 4 months or so. So at least Ulm Institute is not called anymore only Institute of Quantum Biology, but it's called Institute of Quantum Physics and Statistics. So actually, one tries to study how one can excite actually. One can excite. I forgot the name actually of the complex. Does somebody remember the name of it? Yeah, I think that's it.
You mean photosynthesis or when
Yeah,
light harvesting.
light
Yeah,
harvesting
it's
complex?
light harvesting molecule. So there you excite basically. You have this molecule excited on one side, and then the excitation travels from side to side. And there were experiments which actually gave a coherence lifetime of the hopping of these excitations, which was really long, it was picoseconds. And you would think normally it should be maybe a factor 10 or 100 lower. And this coherent transport you can also understand by actually hopping, and then these hopping excitations should excite local phonons, lead to dephasing. And if you calculate the normal rates, exactly like Eugene is mentioning, what you have in organic structures, you got actually in theoretical models always much faster decay. And now actually new experiments actually show that it's actually much faster. But there's again, you can understand this physics also in terms of polars. So it was kind of the underlying scheme of quantum biology in some sense. Okay, that's maybe too negative.
But can you flip this around? So we discussed how electrons can affect excitons. So can there be interesting physics how excitons can affect electron transport?
Thank you, Eugene. This is over here. So what one could ask the following. Let's suppose we have a doped semiconductor with just electrons sitting there, polar repulsion, nothing much going on, it's just a conductor. But then the question is, can we make it superconducting? So we could ask now is, can we build a little heterostructure? Can we build a little heterostructure where we have one layer in which we just have electrons, and can we somehow manage to make this system of electrons superconducting? And what we could do is we switch on the laser, which creates excitons in a different layer, and then the electrons in this layer could actually interact with the excitons. And then the excitons could basically have phonon-mediated superconductivity, mediate interactions between the electrons, and lead to pairing between electrons which were originally not pairing. So that would be, for instance, one way to change the transport properties of electrons in these systems. I mean, there are also different ways. One could think about, then it's a back action. Actually, then they could also go into a crystalline phase. So let's suppose you would have a pristine material if you would have a Wigner crystal, but then excitons might actually destroy the Wigner crystal, changing again the transport properties of the material. So there are a lot of different things you can study how to make a twist to typical phase diagrams of electron gases when you throw in electrons and change thereby then also transport properties in the end.
Good. So, thank you very much, Richard.